Welcome to the AEC class. Now today in the last session we discussed about basic amplifier operation and all, and today let us continue with that. So the question is why the Q point should lie at the center of the active region. So we just explored, we just spoke in the previous class that for an amplifier to operate we have to always set the Q point at the center of the active region. So why the Q point should lie at the center of the active region? So the Q point of the amplifier is set at the center of the active region in order to provide a fruitful amplification. What do you mean by fruitful amplification? The maximum amplification without the loss of signal is known as the fruitful amplification, and pictorially it will be shown on the output characteristics with respect to the DC load line. So that means how do we normally going to get the DC load line? The DC load line is normally drawn by taking the 2 points. One is going to be the maximum VCE, another one is going to be the maximum current. So the maximum current is known as saturation current, and a maximum VCE is nothing but simply VCC for us. So once we get these 2 points, we simply join these 2 points, and once you draw the DC characteristics, we'll be getting the graphs like this for various values of the input current, say 5 microamperes, 10 microamperes, 15 microamperes. We'll be getting the graphs like this, and the Q point will be lying at the center of the active region because of the proper biasing. So by achieving proper biasing, we normally going to get Q point at the center of the active region. So proper biasing means what? VCEQ and ICQ. What is VCEQ? It is going to be VCC by 2. The center of this x-axis is VCC by 2. The center point of this y-axis is nothing but IC SAT by 2. So therefore VCQ is nothing but IC SAT by Q, IC SAT by 2. VCUQ is nothing but is equal to VCC by 2. So this point is nothing but the collection of these 2 points, VCEQ and ICQ, is nothing but the Q point. So this point is known as the average DC line. This Q point is a result of the proper DC biasing. So this line can be treated as the average DC line. So with respect to the DC line, the AC is going to make the excursions. So here the AC, whatever input signal we normally supply, the same signal will be simply propagating at the output by after amplification. So that means here we are going to get the signal without any loss of the signal. So this is normally going to get achieved just by applying proper biasing. So due to proper biasing, the Q point will be adjusted or set at the center of the active region. So this is what the reason why we go with the Q point at the center of the active region. Now when you just simply see the operation of the CE amplifier, the CE amplifier is going to invert the input signal. Therefore CE amplifier can also be called as an inverting amplifier. It inverts the input signal by 180 degrees phase shift. So if you take this as 0 degrees as the point, from 0 degrees, the input is increasing here at the input side. When you come to the output side, the input is simply decreasing with respect to 0 degrees. That means the the input signal is inverted by the inverting amplifier called as a CG amplifier circuit. Now here this amplifier circuit is been shown with the DC supply and also the input signal as V input. Okay. And in the last class we discussed about that this amplifier is providing a gain of say 100 if it is producing the output voltage as 50 volts for the given input of peak to peak of 0.5 volts. Okay, and this is what the circuit we have. Now what is the purpose of R1, R2? What is the purpose of RE? What is the purpose of CB and CC and CE? So the purpose is going to be, the purpose of R1, R2 is known as biasing. For applying proper biasing, we're going to apply the R1, R2. Therefore R1, R2 is known as the biasing resistors, and RE is known as the thermal stabilization resistor. CE is known as the bypass capacitor. CB and CC are known as the coupling capacitors. So these are the various names which we give it to the elements of the amplifier circuit element. Now here in this amplifier circuit, we are normally providing the network biasing. So network biasing is nothing but what? By using R1 and R2 network circuits, network elements, we provide the biasing. Now how we achieve? We just go through achieving of this particular biasing here. So through the by diagnosing the various elements of the amplifier circuit. The elements of CE amplifier are going to be what now? VCC. What is VCC? VCC is nothing but power supply, DC power supply voltage used to supply DC currents and voltages. to the circuit. So VCC supplies DC current to the entire circuit of the CE amplifier. Because of VCC, DC current flows to the circuit. Because of DC current, what happens? A DC proper biasing is normally achieved. How a biasing is achieved? Because of VCC. See here this R1, R2. Now when you simply think of only DC level, when there is no AC signal, what is happening? This DC current is not going to flow through the capacitor, because capacitor is going to block the DC signals, and this capacitor CC is also going to block the DC signal. Therefore, this capacitor CB and CC is going to act like open circuits. Once these two are going to act like open circuit, and C is also going to obviously act like open circuit, when this is also going to act like open circuit, then simply the circuit remains is going to be what now? Simply VCC, R1, R2, transistor RC and RE is the circuit which is normally remained. So this circuit is known as the DC biasing circuit for us. Now this biasing circuit, the elements of the circuit is going to be biasing circuit elements are going to be VCC to supply the DC current, and R1, R2 are known as the biasing resistors used to apply forward bias voltage to the input junction by Thevenin's voltage and resistance. That means if you solve the DC input, if you solve the input circuit, what is the input circuit we have? This is the input circuit we have. Once you look at to the input terminals, this is the input circuit we have. Now once you look at the input circuit we have, once you solve that input circuit, already we did it, we normally going to get a Thevenin's resistance with Thevenin's voltage. What is Thevenin's resistance? Now once you look into this circuit, okay, R1 and R2 are connected in parallel. Why R1 not a current in parallel? Because the current coming from VCC, say I1, is divided into IB and I2. So therefore, since the two different currents are flowing through these two resistors R1 and R2, we call this R1 R2 as the parallel resistors. Since they are in parallel resistors, we simply going to find out the R Thevenin's voltage between the base and the ground as R1 R2 by R1 plus R1 plus R2 by the simple parallel combination of resistance equation. Then next we find out Thevenin's voltage between base and the ground. Thevenin's voltage is nothing but the total voltage, total supply voltage to the circuit into resistance across where we are finding the voltage. So across R2, look at here, across R2, across R, that means from base to the ground, we are finding the voltage. So across R2 we are finding the voltage. Therefore, what is the formula? Total voltage, total supply voltage of the circuit into resistance across where we are finding the voltage by sum of the resistances. What are the two resistors we have? R1 and R2. So therefore, by using that formula, we normally going to find out the Thevenin's voltage as total voltage into R1 by R1 plus R2 is nothing but Thevenin's voltage, and we replace this R1 and R2 with VCC by R Thevenin's with V Thevenin's. And now see this voltage, this positive voltage, this positive battery, this VThevenin is a virtual DC voltage. This virtual DC voltage is applied to the base of the transistor. So it is an NPN transistor. This is P type. To the P type you are applying plus voltage, so it is going to become forward biased. So that means here this transistor circuit, this transistor is going to become forward biased at the input junction by VThevenins. So VThevenins and RThevenins are used to make the input junction forward biased, establishing a low resistance region at the input of the circuit. Hence, this R1 and R2 are used to establish low resistance region at the input circuit. That means in order to apply input junction as forward biased, we normally going to apply R1 and R2. What about output junction reverse biased? The output junction is reverse biased directly by the plus VCC. Plus VCC is directly connected to the collector through RC. Therefore, directly the collector junction is reverse biased. So therefore, the input junction is going to get forward biased by R1 and R2, known as biasing resistors, and output junction is reverse biased directly by VCC. Therefore, a biasing is normally going to get achieved by this particular R1 and R2 and VCC. After this, let us look into the emitter resistor RE. Is used to stabilize the Q point of the amplifier after it is been set at the center of the active region. So by proper biasing, the Q point is normally going to get set at the active region by establishing ICQ becomes equal to ICC, IC sat by 2, and VCEQ becomes equal to simply VCC by 2. So that means what? The biasing current will be flowing through the circuit called as ICQ, and biasing voltage is going to get applied across the collector and emitter known as VCEQ by proper biasing. So by proper biasing, Q point is set at the active region. After Q point is going to get set at the active region, we have to establish or we have to stabilize the Q point circuit, so that we can just simply establish the circuit to have a proper input signal, to supply the proper input signal. So therefore, the emitter resistor Re is used to stabilize the Q point of the amplifier after it is been set at the center of the active region. Then finally, the collector resistor is used to represent the saturation current IC. Okay. Now, what is IC now? This is VCC is applied to the collector by RC. Now the equivalent circuit, how I can simply draw this now? VCC, see this positive of the VCC is connected to the collector through resistor RC. Positive of the supply is connected to the collector C through the resistor RC, and obviously negative will be going to the ground by default. So this is the equivalent circuit we have. So because of the DC voltage, a DC current IC is normally going to flow through the output circuit like this in this particular path. Now if you apply KVL to the output path, so I'll be taking this as the when the loop is going from negative to positive, it is positive. Now drop across this is negative, and drop across this is also negative, plus minus. Conventional current is always going to flow from positive potential to the negative potential. So therefore VCC is positive, minus drop ICRC minus VCE is equal to 0. So therefore from this, what we can simply say it as I can write now VCC minus ICRC is equal to, so VCE, if a saturation current, if the maximum current is flowing through the circuit, then VCE becomes equal to 0. Therefore, IC sat I can write as equal to simply VCC by RC. So that is the maximum current that can flow through the circuit. Whatever may be the input signal that we are going to apply, but the maximum current that can flow through the entire circuit can be represented as VCC by RC. That is the maximum cutoff current that can flow through the circuit. And Re, it can be used, it can also be used as thermal stabilization resistor, normally used to keep the Q point at the center of the active region, irrespective of the increase in temperature, to avoid thermal runaway of the transistor device. So the Re is going to protect the device from thermal runaway. Now, what is thermal runaway? Self-destruction of the unstabilized transistor is known as thermal runaway. So that means self-destruction of the transistor is known as thermal runaway. We have to avoid thermal runaway to happen. So therefore, we connect Re resistor to avoid thermal runaway. Now, how we are simply getting that work done? Let us see. Now, in general, we can say IC is equal to, what is IC is equal to? Now, if you see the transistor basic construction diagram, the current is going to flow from emitter to the collector. So the current reaching to the collector is going to be from the base as well as the electrons emitted by the emitter into the collector. So therefore, I can write this IC becomes equal to alpha times IE. What is alpha? Alpha is the current amplification factor. It is part of the IE. Alpha designates the part of IE reaching to the collector, plus IC naught. What is IC naught? How we read this IC naught? It is the collector to base current when the emitter is open circuited. So it is nothing but when emitter is open circuited, what is the collector to base current when emitter is open circuited? When emitter is open circuited, what is the collector to base current? That is known as the reverse saturation current. In the case of common base configuration, when emitter is open circuited, then what is the collector to base current when emitter is, see the other terminal, there are three terminals, collector, base and emitter. If you omit one of the terminal, then it is called as, it is replaced with emitter by default. So therefore, how can I rate this as collector to base current when emitter is open circuited? So that is called IC B naught is nothing but the reverse saturation current. Now we know the basic transistor current equation, whatever may be, whatsoever may be the configuration, whether it is CE, CB or CC configurations, but the basic transistor current equation is going to be IE becomes equal to IB plus IC, because IE is the emitter current, IE is the source current. So the source current is reaching to the destination IC, is reaching to the collector via base. Therefore, this IE is divided into IB and IC in general. So therefore, I can write IE is equal to IB plus IC, which is known as generalized transistor current equation. So therefore, I just simply solve this equation now by replacing IC with alpha IE plus ICB naught. So by doing so, what I can have here, IE I have here, IE I have here. So therefore, just alpha IE, I'll take it onto the LHS side. Then I can write here alpha IE into, now IE if I take common, IE if I take common 1 minus alpha, I can write I plus is equal to IB plus IC B naught. I can have, so IE is equal to what I can have, IB by 1 minus alpha plus IC B naught by 1 minus alpha I can write. So with this, what we can just say, now we already know a equation that beta is equal to, basically we know alpha by 1 minus alpha is a basic equation. If you add LHS and RHS by 1, if you add 1 to LHS and RHS, I can write beta plus 1 is equal to alpha by 1 minus alpha plus 1. So by doing so, I can say beta plus 1 becomes equal to 1 minus simply alpha I can write. So this IE equation I have, IE is I can, what is IE equation I have? IE is equal to, from this 1 minus, sorry, 1 by 1 minus alpha is nothing but is equal to beta plus 1. So I replace this 1 by 1 minus alpha by beta plus 1 in this equation 1. Plus ICB naught into same once again beta plus 1. So this is nothing but say equation number 2 as the equation for IE. Let us keep it aside. Then say for CE configuration, what I can say, beta as equal to, what is beta? Beta is known as current amplification factor. Alpha is also DC current amplification factor. Alpha, beta, gamma are known as DC current amplification factors. What is alpha? Alpha is the current amplification factor in common base configuration. Beta is a current amplification factor in the common base configuration, and gamma is the current amplification factor in the what? In the CC configuration. So this alpha, beta, gamma are the DC current amplification factors. They will be applied for DC currents, not for AC currents. So what is amplification factor? It is going to be output by input. So what is output current in common emitter? It is collector current is the output current. Base current is the input current for common emitter configuration. So I can write this as change in output current by change in the base current. Now beta is equal to what I can say, delta IC by delta IB. Delta signifies change in the output current. Delta signifies change in the current. So change in the output current by change in input current. Also alpha is equal to what? Alpha is nothing but is equal to, it is for common base configuration. Base is common. When base is common, what is output current? IC. What is input current? IE. So therefore I can have this alpha is equal to delta IC by delta IE. So basic transistor equation is equal to IE is equal to IB plus IC I can write. So therefore, I can just simply extend this with a change in the currents. So delta IE is equal to delta IB plus delta IC. I can have delta IB is equal to, just I can just simply take this IE onto the right hand side. So I can just take this as delta IE minus delta IC. So I want beta actually. So to get beta, how I can get beta now? Beta is nothing but equal delta IC by delta IB, general formula I have. So therefore delta IC by, what is delta IB? Delta IE by minus delta IC I can have. So simply I can just expand this in this particular manner. Okay. Now I divide the numerator and denominator by delta IE. When I divide numerator and delta by, I can just get this equation. Now I know delta IC by delta E is nothing but alpha. So therefore I can just write this as alpha by, this is same, IE by IE, delta E by delta E, these two will get cancelled out each other. Same terms will get cancelled out each other. Then I'll get 1 minus, this is alpha. So I'll be getting an equation beta is equal to alpha by 1 minus alpha as the third equation. So equation 3 is the relation between alpha and beta. So now let us look into the expression for collector current in CE configuration. So this is the general current equation. IC is equal to what I can write, alpha IE plus IC B naught. So IC is equal to alpha IE means what? IB plus IC plus IC B naught. And finally, I can write this as now this alpha IC I can take on the left hand side. Once if I take it, I can write this as IC into 1 minus alpha, okay, plus alpha IB plus IC B naught I can have. Then finally, this 1 minus alpha, which is there on the left hand side, I'll be take onto the right hand side. So I'll divide this on this part and this part, two terms. Then I'll be simply getting this as simply alpha by 1 minus alpha into IB plus ICB naught by 1 minus alpha. So alpha by 1 minus alpha is nothing but beta. Alpha by 1 minus alpha is nothing but 1 plus beta from the previous equation. Then ICB naught as it is. So therefore, finally, what I'll be getting now? IC is equal to beta IB plus 1 plus beta times ICB naught is the output current equation. So what is ICE naught? ICE naught is nothing but collector to emitter current. Collector to emitter current when base is open circuited. In the common emitter configuration, we get this current. In the common base configuration, we normally going to get this particular current. Both of them are going to be the reverse saturation currents for that matter. So therefore, I can write this equation 4. What is equation 4? This is the equation 4 I have. Which is nothing but beta IB plus 1 plus beta times IC B naught. This 1 plus beta times IC B naught I can write as equal to ICE naught. So ICE naught is equal to 1 plus beta times into IC B naught I can write. So therefore IC naught is equal to beta IB plus ICE naught. This IC naught I can write as equal to IC naught. And finally I can write the current equation IC is equal to beta IB plus IC naught I can have. So when anyway, more or less, this is the current equation which we can simply put it over here. IC is equal to beta IB plus ICE naught, where beta IB is nothing but is the amount of IB reaching the collector due to forward bias condition. Okay, amount of the input current IB reaching to the collector terminals is called beta IB. IC naught is nothing but reverse saturation current due to the reverse bias. Okay. So this is the basic current equation which we have. So finally, we should finally derive the H parameter model. So for to derive the H parameter model, we have to apply the AC analysis to the CG amplifier. So earlier analysis is nothing but the DC analysis, where we consider only the DC currents and DC voltages. Now for AC analysis, we always consider only the AC currents and AC voltages. So in order to find out the AC analysis, we assume that the DC conditions are perfectly good. That means what? The DC biasing is properly applied. So once after DC biasing is properly applied, once the thermal stabilization is achieved properly at the DC levels, then we apply the AC analysis. So for AC analysis, we normally going to short circuit all the DC sources. What is the DC source in this circuit? VCC is the DC source. So we simply connect this to the ground. For operating frequencies, AC means what? Frequency will be there. DC means what? There is no frequency. So therefore, when under the operating frequency conditions, the capacitor is simply replaced by the short circuits. Therefore, in the previous circuit is simply reduced like this. VCC is connected to ground. All the capacitors simply replaced by the short circuits. And this N is nothing but the neutral point. Neutral point is connected to the ground, and external voltage is simply applied here in this particular circuit for AC analysis. So therefore, this particular this C collector is simply connected to the ground. See, from collector, the RC, this is nothing but this the B terminal. I can just simply put these two terminals, various terminals as A, B, and C. So this B is connected to ground. That means what? Collector to C to B, there is a RC. That means the C is connected to ground via RC. See here, C is connected to ground. C is connected to B via RC. B is connected to the neutral point. And next one is now A is connected to ground through R2. A is connected to N through R2. A is connected to ground through R2. And next one is A is connected to B through R1. A is connected to B through R1, and this B is once again connected to ground. So that means what, B is connected to ground. And input is as it is, Vs and Rs. What is Rs? Rs is the internal resistance of the voltage source Vs, and this is connected across A and the ground, A and the neutral point. Across A and neutral point, there is a source. And what about RC? RC is simply, output resistor. And what about RL? RL is connected between the collector and the ground and the neutral point. So therefore, RL is connected between these two. Now this is the AC equivalent circuit. This is nothing but the AC equivalent circuit which we have it over here. Okay, now in this circuit, we should draw we should represent various currents and voltages. Now the input current, that is to the transistor, is base current. Base is the input terminal because emitter is common. Base is the input. So IB is the input current, IC is the output current, and the output voltage, output terminal voltage, is nothing but VCE, because collector terminal, emitter terminal, between these two we have VCE. So that is the output collector voltage. Okay, this is the equivalent circuit. Now we replace this transistor by its H parameter model. Transistor T1 is replaced by its H parameter model. How do we replace this by H parameter model? Already we have discussed this H parameter model representation in the previous semester. So therefore, I am directly skipping to the skipping. How do we deduce this H parameter from the transistor? So in the previous semester, we have considered the transistor as a two-port network. From the two-port network, we have deduced various transistor, internal parameters like HIE, HRE, HFE, all these things. So I'm simply replacing this transistor by this particular equivalent model. So apart from this model, everything is same. All the output resistors are going to be same. That means what is between B and C, this is nothing but your transistor. This transistor has been replaced. The physical transistor is replaced by this particular, the AC model, AC equivalent circuit. Now AC, this is nothing but the AC equivalent circuit now. So the internally, there will be some internal resistor called HIE, and internal voltage source is replaced by HREVCE, and internal current source is replaced by HFEIB, and output resistance, output impedance is replaced by 1 by HOE. So this is what the various parameters which we can have it over here. Okay. Now the equivalent circuit, now R1 and R2 is seen as parallel, so I can replace R1 and R2 as a parallel combination of resistors, HIE, HREVC as it is, HFEIB, and 1 by HOE as it is I have, and the parallel combination of RC and RL is nothing but RL dash. I can just have this, and IC is the current entering into the transistor. This is the collector terminal. IC is going into the transistor. Okay, and this is how it is. Okay, now how the current is actually flowing, basically, see here now, this is the input current is coming like this and going into the emitter ground. From ground, the output current is flowing like this. Some part of the current is flowing to the collector terminal, some is going to the load resistance and coming to the ground like this, and once again ground, from ground to the input like this, the current is flowing. So this is what the current flow direction. Basically, for a current to flow, there should be a closed loop path. There is a closed loop path for the current to flow. If you see from this diagram also, you can just designate about the current direction. See, the input current from the source is coming like this. Current is flowing from higher potential and it will be coming up to the lower potential. So current is starting from higher potential. It is coming like this. It is going to the emitter, to the ground. From ground, once again, it is coming to the collector, and collector current is coming like this. Collector current is once again being flowing through the emitter. Okay, and emitter to the ground, and once again from ground is divided into base and the collector current. So like this, the current is flowing. That means the loop current is flowing like this. Now, this is what the equivalent circuit, final equivalent circuit. Now, this circuit is known as the AC equivalent circuit of a CE amplifier circuit. So, this is where we start with. So, from this particular subject onwards, AEC, we're going to start from this particular equivalent circuit. So we assume that the circuit is working very, very fine at the DC level. So if the circuit is fine at DC level, we'll be simply coming to the AC equivalent circuit. So we'll start our analysis from this particular AC equivalent circuit. So in this circuit, there are names given to this particular internal H parameters. This HI is known as the input impedance, input resistance, or input impedance. HF is nothing but the forward current gain, and HOI is nothing but the output admittance. Okay. Okay. Then next IB is the input current due to the AC signal, and HR is nothing but the reverse voltage gain. HR, if HF is nothing but the forward current gain, HRE is nothing but reverse voltage gain. R stands for reverse voltage. Okay, now this the next suffix E is going to designate about the common terminal. If emitter is common, we'll write HIE. If base is common, we'll write HIB. If collector is common, we'll write HIC. Accordingly, HFB, HFC. Okay, accordingly, HOE, HOB, HOC. Accordingly, HRC, HRB, HRA. So that means whichever is the common terminal, accordingly we are going to use that particular term over here for the to designate that it is for that particular common terminal configuration. Okay, so therefore HFE is nothing but the forward current gain in common emitter configuration. HIE is the input impedance for the common emitter configuration. HRE is the reverse voltage gain for common emitter configuration. 1 by HOE is the output admittance for the common emitter configuration. So this is what basically the H parameter model or low frequency H parameter model of the BJT. So we will be starting our analysis from this particular point onwards. Now one thing we have to remember in this particular subject, this subject becomes easy only when you practice. If you don't practice this particular subject, because this subject involves with lot of analysis, so a lot of analysis, that means we should compulsorily go with the electronic circuit analysis. So if you know the analysis, then only you can perform well in the exam. 60 to 70% of the paper in the examination will be based only on the analysis of this analysis of the electronic circuit in the syllabus. So therefore you have to compulsorily analyze the circuit. Okay, so that means analysis means what? Solving the electrical circuit, solving the electronic circuit by electrical means. So therefore, you have to solve the electronic circuit by electrical means compulsorily. So to solve the circuit, you should know the KCL, KVL equations, okay, and you should know some little bit of mathematics, some formulas you should know. So by knowing everything, putting everything together and knowing the procedure and how to solve, then only you can able to solve all these equations. So therefore, you should solve the equations. So by putting pen and paper from today onwards, please try to first of all come to this particular generalized CE amplifier model. So from now onwards, CE amplifier means this is the CE amplifier for us. For exact model, this is nothing but the CE amplifier model, because amplifier is the one which is nothing but application of the transistor. Transistors can be used as a switches or can be used as an amplifiers. When you use transistors as an amplifier, so the amplifier is going to amplify the input AC signal. Therefore, it is nothing but the application. So once you are doing the application, means what? You are simply doing the AC analysis. So here we perform AC analysis only after we perform the DC analysis. So we assume that the DC analysis is perfectly done on this particular transistor amplifier circuit. After DC analysis, we are simply doing the AC analysis. So in this entire subject, in this entire syllabus, we have only AC analysis. So therefore, you have to compulsorily perform the AC analysis. You have to solve the circuits and you have to finally get the output equations by after solving the electronic circuits by electrical means. So you have to compulsorily keep on applying the Thevenin's voltages. You have to keep on applying the nodal analysis. You have to keep on applying the transistor equivalent circuits. Okay, compulsorily you have to come with all these things. So therefore, what is so important is that you have to know this particular BJT H parameter model. So if you don't know the BJT H parameter model, you really cannot do anything in this particular subject. So the mantra or a principle to start with is going to be this H parameter model. So those who got any questions, those who got any doubts, please go back to the previous semester topics of H parameter model and how do we get into this particular H parameter model. That is what the very important point for us to really undergo. And in the coming session, I'll be simply deriving the generalized formulas for the H parameter model. Sometimes he is going to give us the H parameters, all the H parameters, and ask us to find out the amplifier parameters. What are the amplifier parameters? The amplifier parameters are going to be the current gain, voltage gain, input resistance, and output resistance. So these are the various parameters of the amplifiers. So in the examination, a very simple question is the one where he gives us the various H parameters such as HIE, HFE, HOE, HRE. He'll ask us to find out what is the overall current gain of the circuit, what is the overall voltage gain of the circuit, what is the input resistance, what is the overall input resistance, what is the output resistance, what is the overall output resistance of the entire circuit. So these are nothing but parameters of the circuit. Now why we know the parameters? They are known as the performance parameters of the amplifier. We always have to find out the parameters of any circuit or any system to know its performance. So therefore parameters are very much essential for us to find out. So ultimately what we are going to find out is that we simply find out the parameters of the amplifier circuit. So the parameters of an amplifier is very important for us to analyze the amplifier circuit. So we have analysis in the syllabus. Analysis, there are two important things in the electronic circuitry. One is going to be the analysis, another one is going to be the design. What is the difference between analysis and design? In design, we have to find out the circuit components after we know the specifications. Coming to the coming to the analysis part, we'll be knowing the circuit parameters. Okay, we'll be knowing the circuit, and we'll be knowing the input, and then we'll be simply finding out the output of the circuit by knowing the circuit parameters, by knowing the input signal, by knowing circuit parameters, we'll be knowing about the output from the analysis part. So here, these are the two things. That means the design means what? We'll be knowing the input, we'll be knowing the output, but we don't know what is the circuit. What circuit components has to be taken, we don't know. So if you find out the circuit components by knowing the input and output is known as design. So by knowing the circuit components, by knowing the input signal, if at all you want to find out the output, it is normally done by using the analysis part. So we will be doing only the analysis part. And our assumption is that the output is always going to be a stable output. This is the difference between the pulse and digital circuits and ADC circuits. The output of ADC is always considered to be a stable output. So the output of PDC is not considered as a stable output. We have to take from the we have to take output from 0 time period. So we don't wait for the output signal after it gets stabilized. But coming to EDC, we consider only the stable outputs. We don't consider the unstable outputs for analysis of the electronic circuits in EDC subject. In PDC, you have to consider from the 0 time period of the output signal. Therefore, you have to consider transient time as well as the steady state time. So here we have only steady state time period analysis. That means all the analysis whatever you do in this particular AEC, which is known as EDC2, electron device circuits 2 subject, we do only stable state analysis, stable state circuit analysis only. We don't deal with the transient circuit analysis. We deal only with the stable state circuit analysis. So this is what we have, the electronic circuit known as an amplifier. And from next session onwards, in next session we derive the various parameters of an amplifier, and we'll try to solve one or two problems on this. So we start our subject from the next class onwards by doing the analysis of this particular circuit. Thank you very much for the today's session.